All right, so the first thing we want to do is find the limit as x approaches 2 from the left of f of x, where f of x is this piecewise function. So let's think about it. If we're approaching 2 from the left side, then our actual x values are going to be less than 2. So looking at our piecewise function, that means then that we should be using this function when finding the limit, because our piecewise function defines using that function when we're less than 2. This will become the limit as x approaches 2 from the left of x squared plus 6. Is there any reason why we can't plug 2 in for x? Nope, there's nothing that makes it undefined. So even though we're approaching 2 from the left, we are going to just plug the number 2 in. And that'll give us 10. In part B, we're finding the limit as x approaches 2 from the right. So we're looking at values that are slightly bigger than 2. So for the second part, we're going to use our second function. So this will be the limit as x approaches 2 from the right of x to the third plus 2. That's going to be 2 cubed plus 2, which again gives us 10. And then lastly, in part C, we want to find the limit as x approaches 2 in general of f of x. So what we do here is look at our results from our left and our right side limits. If they match, then we know that the limit exists at that matching value, and if they don't match, then we say that the limit doesn't exist. Well, the limit as x approached 2 from the left was indeed equal to the limit as x approached 2 from the right. Therefore, we can say that the limit as x approaches 2 of f of x is that 10. So anytime you're asked to find the limit as x approaches a value, and that value is where your piecewise function splits, you got to do your left and right hand limits and then compare. Questions at all on that?
Ms. Croft, how are we able to use 2 in part A when it says x is less than 2 instead of less than or equal to?
Because, I mean, we're looking at putting in 1.999999999. So, I mean, once you round to an actual number, it's practically 2.
Okay, thank you.
Anybody else? All right, so here is a second piecewise function. I'd like you guys to do this one. I'm going to break you up into groups and give it a try. Notice that the first part of that piecewise function does have a rational function to it, so you may have to do some simplifying before you can plug in. I'm going to break you up into just pairs because there's only 8 of you today. All right, so we'll be using the top function for part A. This is the limit as x approaches 4 from the left of x squared minus 16 over x minus 4. Can we plug 4 in as is?
We cannot.
We cannot, right? Because we'll get a 0. So we're going to have to do some algebra, right? We got the difference of 2 squares here, which we can simplify. So then we're finding the limit as x approaches 4 from the left of just x plus 4. And now it is safe for us to plug that 4 in. And we get 8. In part B, as we're finding the limit as x approaches 4 from the right, we need to be using the bottom function because that's where we define what we use when x is greater than or equal to 4. So this is our limit as 4, we approach 4 from the right. And there's no reason we can't plug in. And we're going to get 66. So we got 8 for the left, 66 for the right. What does that mean for our limit as x approaches 4? Well, it does not exist, and it's because our left and right side limits didn't match. Questions at all on finding limits of a piecewise? Definitely going to be one of those on the test. All right, well, then we're going to move on to continuity. So if we consider the function f of x equals negative 2x squared plus 3x plus 1, we've defined continuity before. A function y equals f of x is continuous if there are no holes or jumps that occur and the graph can be drawn without picking up your pencil. Well, that's not a very technical definition. You know, that's kind of what we went with when we were in college algebra, but we're going to get more specific than that. A function y equals f of x is continuous on an interval if f of x is continuous at every point in that interval. So it might not be continuous for the whole graph, it might just be continuous for a section on an interval. A function y equals f of x is continuous at an interior point, call that point A, of its domain if the limit as x approaches a of f of x is equal to f of a. This is really the definition that we're kind of going to be using here. So if the limit as x approaches a of f of x is equal to f of a, then it's continuous. I want to kind of scroll back where we were doing limits of a graph to look at one where that was the case, and then we'll be able to visually see, sure, it is continuous. Okay, so like this section here, right, the limit, nope, wrong one. Okay, none of them here. Let's check the other graph. All right, here, this set. Notice that the limit as x approaches 4 is the same as our value when x equals negative 4. And if we look at the picture, clearly it's continuous right there. So the limit and the actual value have to be the same in order for it to be continuous. If we jump up and look at what's happening at negative 2 here, clearly that's not continuous because we've got this jump. And if we go back and look at what happened with the limits there, we had two different numbers. The limit was 3, but the actual value was 5. So that's what our continuity definition based off of limits says. The limit and the actual value have to be the same in order for them to be continuous. Now we can have left side continuity and right side continuity as well. A function y equals f of x is left continuous at a point A if the limit as x approaches a from the left of f of x is equal to f of a, and a function y equals f of x is right continuous at some point B if the limit as x approaches b from the right of f of x is f of b. So looking at our little picture here, this is going to have right side continuity because, well, it's continuous as we approach from the right. Here we're going to have a left side continuity because it's continuous from the left. And then we have continuity at an interior point if our limits are the same on both sides. A function is discontinuous if there are holes or jumps that occur and cannot be drawn without picking up your pencil, or if the limit and the actual value are not equal to each other. questions on any of that? Does that make sense at the limits? All right, well, we're going to take a look at this graph here. We're going to determine whether it's continuous at x equals -2, 0, and 3, and we're going to be using like limit facts to back up our answer, not, oh, I had to pick up my pencil when I was tracing it. So let's take a look at x equals -3. Now, calculus aside, is this continuous?
Yes.
So right here, this function is continuous at x equals -2. There's no holes or jumps or gaps or anything.
Well, with the one hole, but the other one's filled, so wouldn't that continue or?
Okay, so if we look at x, if we were just drawing this and we were wanting to say any points of discontinuity, I would say that we were discontinuous at x equals 2 and x equals 3, just because I have holes and jumps at that area. Even if you think back to answering these questions when we were graphing piecewise functions.
Okay.
So, you know, kind of what we're going to do some of the times in calculus is we're going to use our knowledge from college algebra to come up with the answer, but then we need to back it up with calculus.
All right.
All right, so I'm actually discontinuous both of those places, but now I need to back it up with some calculus on why we're discontinuous, not just, oh, I couldn't trace it without picking up my pencil.
Okay.
So starting at 2, well, what's some calculus that could back it up? I'm sorry, at -2. What's some calculus that could back it up to say why we're not continuous?
There is a hole there.
Okay, so that is not calculus. We need to be talking something about limits.
Limit doesn't exist.
The limit doesn't even exist, right? So the limit is x approaches -2 does not exist because the limit is x approaches -2 from the left is 2, but from the right is -1. So in order for it to be continuous, the limit has to be equal to the actual value at that x. But if the limit doesn't exist, that statement can't possibly be true. Is there questions out there? I feel like there's questions hanging. Everybody's okay with that? All right, let's move on to x equals 0 then. So right here is where x is equal to 0. Just looking with your eyes, is this going to be continuous?
Yes.
Yeah, there's no holes or jumps or gaps or anything like that. So we're going to say continuous at x equals 0, but now we want to back it up with some calculus.
Because the limit exists there.
Well, that's not it, though. It's more than just the limit exists. So not only does the limit exist, but the limit has to be equal to the actual value, right? To be equal to the closed circle that's right here. So we're continuous at x equals 0 because the limit as x approaches 0 of f of x is equal to f of 0. Questions on that? All right, now we're going to be looking at x equals 3. Kid's trying to rip my laptop off the counter while it's still plugged in. Jesus. All right, so we can look with our eyes. Is this going to be continuous or not?
No.
No, right? Because we have that hole happening there. So we know that it's going to be discontinuous at 3. Well, now we just need to back it up with some calculus. So what would be the calculus to back it up?
This continues at x equals 3 because limit as x approaches 3 does not exist.
Well, the limit exists because the limit as we approach from both the left and the right approach 0. So the limit exists.
Would it just be undefined?
No, it's not undefined because, I mean, we got a point down there.
Oh, okay. Okay.
We're discontinuous because the limit as x approaches 3 of f of x, which is 0, does not equal the actual value at 3. Right? The limit is one thing, but then there's a hole at the actual value, and the actual value is down here somewhere else, which is what we saw with our eyes anyways, that there was this hole in the graph. So the way that we indicate that with calculus is just by saying that the limit and the actual value aren't equal to each other. This is what questions do we have? This is a pretty important topic, and I feel like people are kind of unsure here.
So what's the difference between that and the first one?
Well,
Yeah.
the first part, the limit didn't exist because the one side was over here and this side was down here. So we can't compare the limit with the actual value because the limit itself didn't even exist.
Okay.
It's true that the limit and the actual value aren't equal to each other, but the limit doesn't even exist. So it's
Okay,
hard to
because
compare. You can't really compare with something that doesn't exist in the first place.
Okay. Okay. I think I can understand.
Anybody else? Well, there are several different types of continuity. I'm sorry, you guys. I need just 1 second to get my kid on his Zoom meeting. I'm sorry.
Uh-huh.
Coming from the left and coming from the right, they both come to a solid point. And then on the far left, coming from the right, it comes to a solid point. But that solid point doesn't connect with coming from the right.
The other point. Okay. Yeah.
When you do the limit, you have to do coming from the left and coming from the right.
Right. Okay. That makes sense.
That was good, Colin. I'm just letting you guys go with it. I like your discussion there. Does everybody feel clarified on it? Yeah, he's right. It's because these aren't connecting here. So if it doesn't connect, then the limit doesn't exist.
Okay.
But here, it, connects. So the limit, where both the left and right side are approaching the same number. So the limit exists. Here, we're approaching one number from the left and a different number from the right, so we can't say the limit exists. The left side limit exists, the right side limit exists, but the limit overall doesn't exist. Just like we were doing even on this previous example here when we were finding the limit of the piecewise function. We found the limit as x approached from the left. The limit as x approached from the right. Because we got two different numbers, we couldn't say that the limit overall as x approached 4 existed. The one before that, the left and the right sides did match, so we could say the limit as x approached 2 overall existed. So back to this picture, the limit as x approaches -2 from the left is way up here at 2. The limit as x approaches -2 from the right is down here at -1. They don't match, so the limit overall as x approaches -2 does not exist. Everybody feel a little bit better? Because again, now is the time to ask all the questions, because your calc teacher isn't going to take all the time in the world. I'm happy to take all the time in the world.
All right.
there's a variety of different types of discontinuity. We have removable discontinuity, which is where we just have a hole in it. That's frequently from a rational function. We have infinite discontinuity, which we could have with a rational, or we could just have with some piecewise, but you'll notice that we do have a rational for the top half of the piecewise. Just means that you're approaching some kind of asymptote. There's oscillating discontinuity, which just means that it's going back and forth so fast that it's like you can't even pick a spot. So like out here, we could name about limits or whatever, but here in the middle, it's just oscillating so fast we can't even pick a point. And then we also have jump discontinuity, which we just end up having just a jump. This is different than our removable discontinuity, because the removable discontinuity, we just have a hole, but the flow of the graph is not changed. Buddy, I think you took it in the living room. You gotta go. This right here, I want to talk about this function here that we have where we have this jump discontinuity. This is a function that we haven't really discussed. What we tend to run into as we proceed in math. This here is called the least integer function. Sometimes it's called the floor function. That's what I tend to call it. That's what I was taught to call it. And what happens with this least integer function is you're always rounding down to the least integer. So like here we have an x value, say it's like a half, but to get the y value, we always round down to the least integer. Even if we're way up here at x equals 0.9, you're gonna round down to the least integer. So that's why everything between 0 and 1 has a y value of 0. And then the same thing's happening here in between 1 and 2. We're rounding all of those decimals down to the least integer, which would be 1 in between 1 and 2. They have it written a little bit differently than I typically write it. The floor function, when I write it, I just have like these bars on the bottom. And that tells me, I feel like that's a visual cue to tell me to round down. And then there's another one that isn't this picture that's called the greatest integer function. Also sometimes called the ceiling function. And what happens with this function is you're always rounding up. So if I put it here on the same graph, the ceiling function would be here. Because you're always rounding up. Even though the x value is 0.1, we're going to round up to the next integer. And this is denoted very similarly, but the bars are up top. That's why I don't totally understand this notation that I pulled out of your book, because, well, how do I know the difference between the least integer and the greatest integer function? So, I just wanted to share that bit with you because you may run across that function in your calculus sequence, and I don't want it to be something you've never seen before. All right, we'll talk more in calc about all these different kinds of discontinuity. I just, again, wanted you to see it before you got there. We're going to be using a test to determine whether something is continuous at a particular x value. In order for a function y equals f of x to be continuous at x equals a, these three things have to happen. First, f of a has to exist. Second, the limit as x approaches a of f of x has to exist. And then thirdly, those first two things have to be equal to each other. So that first part of the graph where people were having trouble on why it didn't exist, you know, it failed part 2 of the test. The limit itself did not exist. For one-sided continuity, the limits in part 2 and 3 of the test should just be replaced by the appropriate one-sided limit. So we use the continuity test to determine whether f of x equals x squared minus 5x plus 6 is continuous at 4. So we got to do three things. First, we need to determine, does f of 4 exist? I think my tablet's tired from all of the videos I made in the last couple days. All right, so does it exist? The only way we're going to figure out if it exists is by simply plugging 4 into f of x and making sure that we don't get something that's undefined. So it's a 16 minus 20 plus 6. We get 2. So we didn't get something undefined, so that means, yeah, f of 4 exists. Second, we need to determine if the limit as x approaches 4 of f of x exist. So this is the limit as x approaches 4 of x squared minus 5x plus 6. Is there any reason we can't plug 4 in right now?
No.
Right, so let's just plug it right in. 4 squared minus 5 times 4 plus 6. That's going to give us, again, 16 minus 20 plus 6. That's going to be equal to 2. So it does indeed exist. And then the third part of the test, does f of 4 equal the limit as x approaches 4 of f of x? So we just take a look. And they do. Therefore, f of x is continuous at x equals 4. Questions? All right, let's try another one. We want to use our continuity test to determine whether f of x equals x plus 7 over x minus 7 is continuous at 7. First thing we want to do is see, does f of 7 exist? And the way we figure this out is simply by plugging 7 into our function. I get 14 over 0, which is undefined. So does f of 7 exist? No, it does not. So I'm not even going to waste my time doing the rest of the test because all three things have to happen. So if this first one doesn't happen, I'm not going to waste my time with the rest. I'm going to simply conclude at this point, f of x is discontinuous at x equals 7. You know, honestly, with the first two steps of the continuity test, you could do it in whatever order you prefer. I always prefer to do the does the f of 7 exist because I think it's easier than finding the limit. Sometimes the limit can be more involved, so I always do the easy one first because if it doesn't work for that, then I'm not going to spend time doing the limit. Questions, anybody?
So the fact that it says it is continuous at 7, that 7 for the limit then will be the x approaches 7?
Yep.
Okay.
So whatever they tell us. In the first one, they said 4. Is it continuous at 4? So that's what we're using for our x. In this one, they're using 7. So that's what we're using for our x. Anybody else? All right, let's try one more, this time with the piecewise function. We want to use our continuity test to determine whether this piecewise function is continuous at x equals 1. And notice 1 is where our piecewise breaks up. All right, I'm gonna let you guys do this. I'll break you up into rooms. Heads up here, because you're going to be finding the limit as x approaches 1, and 1 is where our piecewise function splits, you are going to have to do left and right side limits, make sure they match when you're looking at determining whether the limit as x approaches 1 exists. Did I leave before I could put you in room? What was that? All right, I like 4 rooms again. Okay. All right, so resume recording. Here we go. So the first thing was we wanted to see if f of 1 existed. F of 1 is equal to exactly 1. Second, we wanted to look for the limit as x approaches 1. We had to do both the left and right side limit, and you got 1 for both. So we got that the limit was equal to 1. And then lastly, we need to make sure that the limit as x approaches 1 of f of x is equal to f of 1, and it was. So we were able to conclude that f of x is continuous at x equals 1. Questions? Anybody? Everybody seemed to be pretty good. All right, so some other things we like to do, other than just test for continuity, is determine where it would be discontinuous. You know, what are the intervals that we are continuous, or what are the intervals where we're discontinuous? And we're automatically discontinuous if the function doesn't exist. We're automatically discontinuous if there's any type of asymptote happening, and we're automatically discontinuous if the limit doesn't exist. We're automatically discontinuous if the limit and the actual value don't match. So let's look at this first one. Right? F of x equals x squared plus 3x over x. What do we know about this function?
Can you simplify the whole thing by x?
It can be simplified. So when you simplify a rational function by canceling out a common factor, what does that mean for the graph at that point?
Oh,
There's a hole there. Or personally, I would just look at this and say, oh, it's rational. It's going to be continuous everywhere on its domain, because the limit I know exists everywhere on its domain by that theorem that we had earlier. So if the limit exists everywhere on its domain, all I have to do is figure out what value is excluded from the domain, and that's going to be the only spot that it's discontinuous. The only number we would have to be excluding from the domain is x equals 0. So that's the only place that we're discontinuous. So Victor, you weren't wrong. It was just way more work than we needed to do. Questions on that? So if it's rational, just set the denominator equal to 0, solve, and those will be your points of discontinuity. Now, there's different ways to word the same question. They might ask you to determine where it is continuous. So we could either write that in interval notation, or maybe in set builder notation. And if we did it in set builder notation, we'd say it's continuous for the set of all x such that x does not equal 0. Now, in the past, I've kind of said, oh, set builder, it's not so helpful. It's not so helpful till we get to later. Well, we're approaching that later. So set builder notation can be really helpful for these types of problems. Questions at all? All right, let's try a couple more. Now we want to find anywhere that this function is discontinuous. What do you know about tangent?
Y over X.
That's true. It is y over x. What do you know about the graph of tangent?
It's a squiggly line.
It is. I agree.
They all are.
But there's a bunch of them, right? And what are they separated by?
Asymptotes.
Asymptotes. So where tangent is discontinuous is where all of those asymptotes are. But the asymptotes repeat over and over and over again. So we have to come up with a way to indicate where all those asymptotes are. So here, I'll put this on the Cartesian plane here quick. We know tangent is 0 at 0. What's the period for tangent?
Right.
Pi. So this is going to be pi over 2 here, and this is going to be negative pi over 2. And then the next asymptote, right, is a distance of pi. So this is 3 pi over 2. And then the next one's at 5 pi over 2. Well, I can't possibly write out every single asymptote to infinity. So we'll say that we are discontinuous at, we'll start with our first asymptote of pi over 2. And now to indicate that we're discontinuous starting here and then adding a period of pi over and over and over again, we're going to be discontinuous. We say plus pi n, where n is an integer. And that's going to get us all the asymptotes going both to the right and to the left, because we know integers could be positive or negative. Questions?
How would it look like if it's sine or cosine?
Well, sine and cosine aren't discontinuous, right? There's no breaks, no asymptotes or holes in it. Now,
Oh.
cosecant, we would have to then find the asymptotes, and they're going to differ by pi as well. So you'd find the first asymptote and then just a period of pi, as long as the argument is x. If they start changing the argument, well, then that period's going to change. You're going to have to do your pi over b.
Okay. Okay, thank you.
Anybody else? All right, let's take a look at this piecewise function. We have to figure out where it is discontinuous. Well, really the place we only have to watch out for is where it's broke up. So in order for this to be continuous, that means that the left and the right hand limits have to be equal to f of 6. So we just want to take a look and see, because I know it's not going to be discontinuous anywhere else, because 7x is a line, so that's not discontinuous. X squared plus 6 is a quadratic, a polynomial. That's not discontinuous anywhere. So the only place we could possibly have a problem is at 6, where everything is meeting. So we'll just take the left and right hand limits. If we get anything other than 41, since that's our actual value at 6, then we know that we're discontinuous at 6. So let's do the limit as x approaches 6 from the left of 7x, we're just going to plug in our 6. And 7 times 6 is 42. I don't even need to check the other one. It's not equal to 41, which is the actual function value at 6. So f of x is discontinuous at x equals 6. Questions at all? All right, so I see I got ahead of myself because I was just recording all these videos for pre-calc and clearly didn't remember what we had actually talked about and what I had talked about in my videos. So here's this theorem that I've referenced like 3 times today that we haven't actually hit yet. The theorem says that the following types of functions are continuous at every number in their domain. Polynomials, rational functions, root functions, and trigonometric function. So sorry about that. So now we want to determine where it is continuous. So basically, we just need to state the domain. So here we have a polynomial function. What's the domain? You're making it hard. What's the domain for every polynomial?
Negative infinity to infinity.
That's right, all real numbers. Remember, our domain is all real numbers unless we have a variable in the denominator, a variable under an even indexed radical, a variable in the argument of a log, and then we got to watch out for our trig functions. So let's look at the next one. F of x equals x minus 5 to the 1/4. The first thing I would do is I would rewrite this. We know that an exponent of 1/4 is the same as the 4th root. Here we have a variable under an even indexed radical. So to find the domain, we're going to set it greater than or equal to 0. So x has to be greater than or equal to 5. We're going to be continuous on the domain, which is 5 to infinity. Questions? I need 5 minutes. All right, just 2 more. I just want to finish up this section so we can start derivatives Friday. All right, now we have a rational function. What do we need to do to find its domain?
Set the denominator equal to 0.
You got it. Set the denominator equal to 0. Solve and exclude. We're going to get x is plus or minus the square root of 1. So we need to exclude plus or minus 1. So we're going to be continuous from negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. I saved the best one for last. But the greatest thing about math is even when it gets complicated, the rules are the same. So our domain is all reals unless we have a variable in the denominator of a fraction under an even indexed radical in the argument of a log, or we kind of have our trig functions as their own separate category. Well, there's no trig functions, there's no log, so we only need to deal with a variable underneath an even indexed radical, and then I have a variable in 2 different denominators. So I just need to deal with each one of these things independently and then bring them back together. So starting with the square root of x, we know our radicand has to be greater than or equal to 0. Well, that's already solved for us. For our first denominator, we set our denominator equal to 0, solve and exclude. so we can't be equal to 1. And then we have our third denominator. Again, we're going to set it equal to 0, solve, and exclude. And we get x equals plus or minus the square root of -1. This is imaginary. Well, we know that we don't have imaginary numbers on the Cartesian plane, so this does not yield an additional exclusion. So all we're dealing with is x is greater than or equal to 0, but it can't be equal to 1. We could draw this out if we wanted to help ourselves. So I can't be 1, and then I've got to be greater than or equal to 0. So what's our interval of continuity?
Zero, 1. And then 1 and infinity.
There you go. Perfect. I like that question. I'm going to try to find one of those for our test. So, yeah, that's it on continuity. Any questions at all? All right. Well, on Friday, we're going to talk about derivatives, which is, the basics of Calc 1. I don't know. I'm feeling like that might take us more than one day. Our test might not end up being until Friday next week. We'll just see how it goes. This is just so important. I want to make sure that I'm taking my time and really covering it thoroughly with you guys. All right. If nobody has any questions, I will see you on, I don't know what day it is. It's day Wednesday. I'll see you on Friday.
Bye, Allison. Have a good
Bye.
day.
Have a good day, everybody.
Yeah.
Have a good one.
Uh,
I say hi from space.
All right.